Hi students, we are going to talk about the processes of mathematical reasoning in this PowerPoint. This is one of the longer PowerPoints, so bear with me, but to me this is one of the most important ones because it really establishes not just the math that students should be learning in the classroom, but more so how they need to be learning it. So we've talked about the Common Core Standards already, but the Common Core Standards essentially are asking students to have a real understanding of mathematics rather than just kind of that surface understanding that you and I probably got when we were in elementary and high school. We want students to learn new math concepts through problem solving rather than just having, people show them methods of doing problems. So a lot of times I refer to this development of new math concepts as sense making. So, one of my mottos is math should make sense, and if it doesn't make sense, something isn't going right. So we are really used to being students and being asked to perform mathematical tasks. We all know what a math test looks like. Essentially it's a set of problems and we just follow the steps that we were taught in class and hope that we don't make any mistakes and hope like heck that we actually remember the steps. But, we are wanting a lot more out of students now. That's what the Common Core is all about. So we're not used to what it means to watch students making sense of mathematics. So it's really difficult to know, well, what does that look like and how do we know if it's actually happening? This is a topic we could spend an entire semester on and probably more. Obviously, it's way beyond the scope of this course, so we're going to kind of keep it small and focused on just something that we can accomplish in a short amount of time. So the aspect of sense making that we're going to look at is how students make conjectures and how students justify, and kind of the dirty word that goes with justify is prove conjectures. And I say that's a dirty word because most people, if you say the word proof to them, they kind of have flashback nightmares to high school geometry, where proofs were something that they were kind of drugged through kicking and screaming. So making conjectures involves, reasoning about what you see is happening and developing generalizations or statements about things that you are seeing. And conjectures are tentatively thought to be true, but they're not known to be true. They're not written in stone. So inductive reasoning requires being able to identify commonalities, being able to say, hey, I notice these things, I see this pattern or this relationship, and I'm going to expand that pattern or relationship to make this conjecture. And this kind of reasoning is called inductive reasoning. So for inductive reasoning, it involves going from a series of specific cases to a general statement. So again, looking at a lot of examples and spotting the pattern and making a general statement about that. Inductive reasoning is the type of reasoning that is used to make conjectures. So all conjectures come from inductive reasoning. So here's an example. So imagine that you are a small child and you probably hopefully have someone in your life where you've seen a 2 or a 3-year-old and they love to point at things and give them names. So they might say cat, 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 and they point when they see animals. And eventually they get to the point where they can distinguish between a cat and a dog and a fish and all sorts of different animals. They do that pretty quickly actually. So let's say, a small child has come across cats in books, on TV shows, in real life, and they make a conjecture that all cats have tails. We can see where they could come up with that conjecture pretty easily. That's the experience they've had. Every cat they've ever seen has had a tail, so they make this conjecture. All cats have tails. So here's the big question. Is a conjecture always true? Well, what do you think about this kid's conjecture? All cats have tails. When we talk about conjectures, there is a way that we can be certain that a conjecture is false, that we know without a doubt a conjecture is false. So right here is my what we call a counterexample, which is essentially an example that says, hey kids, sorry, but that's not a true conjecture. Not all cats have tails. So this is a picture of the disabled cats that my daughter adopted. And you can see this one's Scooter in the front. He's got a tail, but Thumper, no tail, but he definitely is a cat. So Thumper is a counterexample, and it only takes one counterexample. So I can have a small child say, hey, all cats have tails, and I only have to show him one cat that doesn't have a tail to help him know that his conjecture is false. It doesn't take more than one counterexample. So then on the flip side of that, how can we be certain that a conjecture is true? Well, that's a lot trickier. There essentially is no way to do that just by looking at cats. So I could show this small child cat after cat after cat, and it might seem that his conjecture is true, but then there's always going to be kind of that thought out there, well, what if we just haven't seen a cat yet that doesn't have a tail? And maybe some of you have never seen a cat that doesn't have a tail, and we're surprised that this conjecture is false. The thing with conjectures is you can be pretty sure they're true, you can feel that they're true, but you need to understand that conjectures can only be true when they are proven to be true. And that takes a different type of reasoning. So justifying or proving conjectures to be true involves making a logical mathematical argument based on things that you already knew to be true. And you experienced that in high school geometry class. Perhaps you remember, or perhaps you have completely blocked out making those T-charts where you would list a step in the left-hand column, and in the right-hand column you would list the name of the theorem. Those were the already understood ideas, and you were logically connecting those steps and those theorems to prove something new. So it does not involve showing that a conjecture is true for one or a few examples, or even a ton of examples. A proof is explaining why a conjecture is true for all examples. And you can't ever show all examples because that's infinite. So you have to be able to explain why you know that it's true for all examples. This is a different type of reasoning. This is called deductive reasoning. So for deductive reasoning, it involves going from a general statement to a specific instance. So it's the other direction from inductive. You start with something that you know to be true, and you draw a conclusion based on that truth. So here's an example. So a child is taught a true statement. Triangles are polygons with 3 sides. And a child concludes when they see this blue shape here that it's a triangle because it fits the definition of polygon that they've been taught, and it has 3 sides. So that is a student saying, hey, I know what a triangle is, and I can look at this and say, yes, this meets the bill. So deductive reasoning is used to justify and prove conjectures. So this is worth saying over and over again. Inductive reasoning, you make conjectures. Deductive reasoning is used to prove conjectures. So a conjecture, until it's proved, is just that. It's just a conjecture. It's kind of hanging in the air. So this is something that I think is really interesting, and I like it because it's not that complicated. We can all understand it. So there's this conjecture called Goldbach's conjecture. And it's been around for years. And essentially, this guy predicted that every even number, so like 6, 8, 10, can be written as the sum of two odd prime numbers. So you have to know what prime numbers are. Prime numbers are like 3, 5, 7, 11, numbers that don't have any factors other than 1 in themselves. So you see some examples here. 3 plus 3 is 6, 3 and 3 are both prime, 5 and 3 is 8, prime, etc. Well, here's the cool thing. So there are brilliant mathematicians in this world, yet the conjecture has been tested and found to be true for numbers into the trillions. So you can imagine somebody writing a computer program and essentially, over and over and over again, they keep getting bigger even numbers and finding two odd primes that you can add together to get it. But no computer program can ever test every number because that's infinite. And no mathematician has yet been able to come up with a counterexample, which would disprove it, nor have they been able to come up with a formal proof. And remember, that's an explanation of why we know for sure it's true for all examples. So I just think that's a really cool thing to think about, that there's still conjectures out there that have not been proven. So this is a diagram. I like diagrams a lot. And I want you to think of this as an onion. So getting students to be able to write proofs is the goal. But, we've got to start small. So essentially, you start small. And this smallness here kind of starts in even pre-K, kindergarten, first grade. And I call it discerning differences. So it's just noticing that some things are different. They're, these things are red, these things are blue. These things are circles, these things have square sides or straight sides, that kind of thing. So this is thick, this is thin, this is hard, this is soft. I think you get my drift there. So once students get good at that, then they can start spotting a pattern. And they can do that in first and second grade and so on. And then the next layer upon that is, hey, I spot a pattern and I make a conjecture about it. Once students make a conjecture, then, they often, if you've got the right kind of classroom, and I hope you will, you'll have students all the time making conjectures. Things like, hey, is it true that an odd number plus an odd number is always an even number? Stop for a minute and think about that. Is that true, that an odd number plus an odd number is always an even number? And you want them to shout those out. And then you want to throw it out to the class and say, hey, class, is that always true? And see if they can come up with a counterexample. They're going to want to prove each other wrong, so they'll look for counterexamples. If they can't find counterexamples, they're going to prove, and see how I have that in quotation marks, proving. They're going to try to come up with a bunch of examples and say, hey, this is true because I can't find a counterexample. That's still inductive reasoning because it's not a proof, but it's moving that way. Then the next layer is what we call proving a conjecture by a concrete example. And there'll be more details on that later. And then beyond that is proving a conjecture using deduction and logic. And that's that formal proof that you learned in geometry. You don't have to use a T-chart, and we're not going to use that in this class. But there are ways to write formal proofs where you're essentially saying, hey, I know this is true for all instances. All right, I'm going to pause here, and I'm going to then start this again with a second recording. I'm almost at the time limit on my recording. Again, I know that this is a long one, and I apologize for that. I'll be back at you with part 2.